Okay. So, with this x3 xc3 value we will compute this, we will compute all the values such that look, two methods load flow we have used, and one shunt capacitor some example I have given, and one this one we have also given this thing, right, very simple thing. So, flat voltage start. So, in this case we are taking same thing, that 1 angle 0 for all the voltage. So, initially if it is flat voltage start, all these things initially have been calculated, it is series capacitor. So, I 2 is equal to 0.004 minus j 0.003 per unit. Now, it is understandable to you. I 3 is equal to 0.005 minus j 0.004 per unit, and I 4 is equal to 0.006 minus j 0.004 per unit. Now, same way I 1 is equal to calculate I 2 plus I 3 plus I 4. If you calculate, it will become 0.0186 angle minus 36.25 degree. I 2 is equal to I 3 plus I 4. If you do so, it will become 0.01636 angle minus 36.03 degree, and capital I 3 is equal to small I 4, that will become actually 0.007211 angle minus 33.69 degree, right. Next is that your V2 calculation. So, same is V2 is equal to V1 minus I1 Z1 1 angle 0 degree. So, put this V1 is 1 angle 0, right, is equal to I1 value you substitute, and your Z1 also you substitute, right, and simplify. So, you will get V3 is equal to 0.96718 angle 0.36 degree per unit, right. So, similarly V4 is equal to V3 minus I3 Z3. So, same as before, first your V3 you got this one, V2 you got this one, V3 is equal to this one, you substitute, you will get this one, right, and V4 also you just substitute I3 and Z3, right, because Z here is decreased, it is 1.8106 angle 1.6 degree. So, in this case V4 case you just do it and simplify, you do all calculations and simplify, you will get V4 is equal to ultimately 0.95619 angle 0.78 degree, right. This is your after first iteration, Now, second iteration starts here, this is second iteration. So, with this new voltages, right, we calculate I 2, I 3 and I 4. So, just you substitute all these things, PL minus JQL is equal to your divided by V conjugate, this formula, you put it, you will get this value 0.00406 minus j 0.003035. Similarly, I 3 is equal to same thing divided by your V 3 conjugate, whatever it is there, right, you will get 0.0051928 minus j 0.004101, right, and similarly I 4 you calculate, right. So, I 4 if you calculate, this is don't take, this is don't take, right. So, here it is 0.00754 angle minus 32.91 degree, right. So, this way small I 2 in second iteration you got. So, second iteration you compute capital I 1. So, you will get 0.01921 angle minus 35.78 degree. Similarly, capital I 2 will get small I 3 plus I 4, that is 0.0115228 minus j 0.008198. So, it is coming 0.01414 angle minus 35.43 degree. Similarly, I 3 is equal to small I 4. So, it is the same value of I 4, this value. Therefore, you calculate V 2, right, you put all the value I 1, V 1, Z 1, everything you put, you will get V 2 is equal to 0.98578 angle 0.084 degree. Similarly, V 3 is equal to V 2 minus I 2 Z 2, put this V 2 value here and this I 2 and Z 2 value here, right, and calculate. You will get V 3 is equal to ultimately 0.96591 angle 0.36 degree, and this is your in what you call your real part, and this is imaginary part of this one, right. And this V 4 is equal to V 3, this value you substitute, right. So, V 4 is equal to V 3 minus I 3 Z 3. So, that is your V 3 I 3 and Z 3 here it is decreased value, right, because of that series capacitor. So, if you solve it and do this, that V 4 will become 95431 angle 0.79 degree per unit. Now, this is after second iteration. After second iteration with series capacitor, this is the voltage. Without series capacitor, that is at the very first load flow studies method 1, this value rewriting, it is 0.98578. Here also look 0.98578, almost no change in the voltage, even almost no change in the angle here 0.085, 0.084. Similarly, look this one 0.96590, 0.96591, almost no change, almost unchanged, it is unchanged, right. And if you look at this one 0.95137, but this is 0.95431, but here it is improved, here it is 137, here it is 431, the voltage has improved, because I told you at the beginning that series capacitors you have connected here. So, voltage will be improved here, but here and here it will remain unaffected, right. There will be no change in voltage, almost it will remain same. So, I suggest that you put the same value of the capacitor in branch 1 and please try to see the your what you call that what is happening to the voltage V 2, V 3, V 4. You will find without any series capacitor, you will find here voltage will improve, right, all voltages will improve. So, this is what your what you call that your series capacitor. With this, now again I will come back to that your regarding some explanation that regarding use of your shunt capacitor. Just hold on, that your before this thing, these are the point, right. These are the point that your first thing is that if you economic justification for shunt capacitor. Here look, here you try to understand certain things, that although it is not possible to solve in the class all these things, but some ideas you have. First thing is release generation capacity. This is actually what happened, that you think like this. I am just telling you, just listening, just listen that. Suppose a generator, suppose in power plant is synchronous generator, right. So, it generates power, real power as well as your reactive power is also required. Basically, its rating is in terms of mega MVA. So, whenever you are putting shunt capacitors your on the distribution side, that means you are compensating basically kilovar, right, or megavar whatsoever. So, that means the network is actually not drawing that your whatever compensating you are putting, network actually not drawing any reactive power from the your source. So, if I assume that if it is so, then what will happen, then in the as it is telling that it is release generation capacity, that means that on the side of the generator, that it need not supply all the reactive power to the load, because something you are compensating. So, naturally generator in terms of generator MVA capacity, that MVA will be released, because generator needs less MVA as compared to without shunt capacitor. So, that is why actually it is called release generation capacity. Second thing is release transmission capacity. The idea of release transmission capacity means that in the transmission line, that you have different type of conductors, right. You have different type of conductors, and every conductor has its thermal capability, that is the maximum current carrying capacity or maximum temperature rise. So, whenever you are putting capacitors, that means reactive component of the current is getting compensated to some extent. That means magnitude of the current on the transmission side will decrease, right, will decrease. So, that means that means other way actually that transmission line or transmission network, right, will be less loaded compared to having without any your shunt capacitor. So, that is why it release transmission capacity means actually it is basically that network loading or transmission line maximum current carrying capacity, whatever it has, it will carry less amount of current, right, compared to that. That means transmission line can be further loaded, because it will draw less amount of reactive component of the current through the transmission line because of the shunt capacitor. Now, third thing is the release distribution substation capacity. So, I told you that in distribution system, as soon as you connect the your what you call that your reactive power support, that is shunt capacitor, then what will happen, that substation, from the substation it will draw less reactive power. Therefore, if it is so, then it is releasing distribution substation capacity. That means apparently that as if substation capacity will increase, because distribution system substation, the transformer is there, and without capacitor whatever transformer supply KVA was supplying, because of the shunt capacitors, that KVA supply will be reduced because of this shunt capacitor, although real power will remain same, because we are not compensating any connecting any real power devices like such as distributed generation, but reactive power. So, that is why it will release the distribution substation capacity, because transformer loading will be less, because it will supply less reactive power, because you have shunt capacitors on the distribution side. Now, additional advantages, one is reduce energy losses. So, naturally I square R loss will reduce, and sometimes I make one English rhyme type of thing, that energy is power multiplied by hour. So, whatever power losses will be there, multiply by time. So, that will be your energy loss. So, naturally as I square R loss getting decreased means basically energy loss is getting decreased, right, because system is on for 24 hours. They reduce voltage drop and consequently improve voltage regulation. Naturally, if your voltage, because of shunt capacitor, the reactive component of the current is getting decreased, therefore, that in the line the voltage drop will be reduced, hence the voltage will, though not much, but voltage will improve. So, naturally voltage regulation will be better. Then release capacity of the feeder, that is another thing, the same like a releasing transmission system capacity. The here it is distribution side, there it is transmission side, meaning is same. That means your distribution line or distribution feeder, because of the shunt capacitor, the reactive component of the current will decrease. Therefore, its current your carrying capability will increase in the sense that you can add more load, right, because of the, because it will draw in magnitude wise it will draw less amount of current because of the shunt capacitor, right. And these are, I have told you, postponement or elimination of capital expenditure due to system improvement or an expansion due to this, all this reason. And the revenue increase due to voltage improvements, that because voltage is improved, really energy consumption will be better, right. So, naturally revenue increase due to this thing will be more. But let me tell you one thing, that distribution actually as an engineer actually what you will look into, you will look into how much you are investing and how much actually revenue being generated or collected, right. So, basically difference of this thing will be gain or loss whatsoever. So, whatever, suppose if you are an utility, then you will see how much energy is from suppose at the your what you call, how much energy is generated and how much money you have collected from the consumers. If you see that this difference is positive, that means you are gaining, and if you see it is negative, means you are what you call, you are a loser. So, as an engineering point of view, you will see that how much you have invested and how much you have earned, right. So, here also same thing, how much energy is generated and how much revenue is collected, because everything actually matters in terms of money. So, that is why that and in the distribution side you have thousands of feeders, 11 kV feeders mostly, right, and particularly India and many other countries, this 11 kV feeders. So, there will be heavy power loss, particularly in the distribution side, I square R loss, technical and non-technical both losses are available, they are there, right, but our concern here is only that technical losses. So, these are the certain things, but you have to do the proper design of the distribution system. Now, before closing this distribution part, few things I would like to tell you, then we will move to the different topic. One thing is, generally whatever you see, that suppose you have this kind of distribution network, right. Coding writing for this one, for distribution side, is not difficult one, it is quite easy, right. So, suppose you have this kind of network, some lateral branches I am taking just for the purpose of explanation, this kind of network I am taking, and suppose node number, this is your substation. Substation means I told you that it is coming from the grid, right, and this side I have told you at the beginning, this side may be your this side may be, I mean this high tension side, it may be 33, maybe 66, maybe 132 or maybe even 220, right, but ultimately it is stepping down to this side is 11 kV. So, suppose this is substation, this is node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8, node 9, say node 10 and 11, 12, say this is 13 node, everywhere load is there, although I am not showing, but everywhere load is there, everywhere load is there, right, everywhere load is there. Now, what I want to tell, that basically there are three types of load or composite type of loads are available. One is constant power, one is constant current, another is constant impedance. So, I will put a question to you and you will write to email, give one or two examples of constant power load, give at least one example of constant current load, and give one example of constant impedance load. Of course, constant impedance load I will tell you here, right. So, if you have any other thing you can let me know, right. So, basically what happens, this capacitor actually it is a constant impedance device, generally that it is connected to the your what you call frequency of the system. If it is a 50 hertz or 60 hertz, that frequency is generally not changing that way, right. It is around nominal frequency, but sometimes little less than 50, sometimes little more than 50. right. So, so that means it is a basically constant impedance type, because reactance of the shunt capacitor will remain constant, right. So, in that case what happens, suppose you are buying capacitor, so manufacturer will give you say a 5 megavar capacitor, right, and they will say nominal voltage means suppose if it is written say 33 kV, right, it is a nominal voltage. So, if I take 33 kV or 11 kV whatsoever, right, it does not matter. So, ultimately it will give megavar, it will kV. So, if you convert it to per unit, so basically 5 megavar will be there. So, let us say 33 kV or 11 kV whatsoever, whatever way you write, right, that manufacturer will give like that. Means that if the voltage level at the time, if it is a 33 kV, then only 5 megavar will be injected. If it is more than 33 kV, then it will inject perhaps more than 5. If it is less than 33 kV, it will be injecting less than 5, but right. So, basically it is a constant impedance device. That capacitor is a constant impedance device. That means, suppose initial value, if something is given like this, manufacturer say QC 0, therefore, your actually Q will be QC 0, then magnitude of the voltage square. That means, suppose this is the node where voltage is there, and here you have here capacitor is connected, right, it is QC, this is the voltage, right. Therefore, where it is connected only that point voltage, it will be QC 0 V square, that is your this one, why it is coming V square proportional to, I will ask you to do this 3-4 lines equation and see any book, it is there. I am not doing it for you, you should write like previous power system analysis course, those you have taken. I put many things, many of them solve it. This is 3-4 lines. I will not mention the book, which book it is there, then you should find out. Every textbook you will find this, right. But this thing you have to understand, that it is V square, that it is per unit, V is a per unit, QC 0 also per unit, it does not matter. Even if it is per unit or even if it is kilovar, megavar, it does not matter. This V is also this thing. So, how things will happen? For example, suppose if V is equal to that mod V is equal to 1.0 per unit, that is if it is 11 kV or 33 kV, it will be 1 per unit means 11 or 33. That means, your Q should be is equal to QC 0, that means exact var will be injected. But if it is not, suppose mod V is equal to at particular node 0.95 per unit, that means your Q should be is equal to QC 0, then it will be 0.95 square, right. That means, suppose for example it is 5 megavar, then if you take it square 0.95 square, I do not have calculator or how much it will come, you calculate, that means that amount of thing it will your what you call, it will inject. That means, for example, suppose if it becomes say for example 0.85 or 86, that means if it is a 5 MVA megavar, right, then 0.86 into 5. So, that means roughly 4.3 megavar will be injected instead of 5, because capacitor actually it is a constant impedance type of load. That means, wherever example we have taken, we have connected a capacitor of 400 kilovar. So, that does not mean that it is injecting, although from the, because there I have treated everything as a constant power, that is why I have taken everything, right. If I try to do constant impedance of capacitor and other composite load, it will be difficult for the classroom purpose. So, that is why if your manufacturer rating will be like this, but ultimately in reality it will inject less. But if voltage goes more than that, if you say voltage goes 1.01, it can also happen, does not matter. So, in that case it will be little bit more, it will inject, but in general case it will be less. So, whatever 5 megavar you thought it will give, it is not, therefore, you need exact analysis by treating the capacitor as a constant impedance load, right. So, this is one thing, that why it is constant impedance load, you will write that 4, I think it will take 1, 2, 3, 4, 5 lines, 5 or 6 mathematical equation. If you write a small equation, you will get it, this one. This is one thing for the your what you call for the shunt capacitors. Now, another thing is, although beyond the course, that DG thing also I have told, distributed generation, at least the concept I have told, but we will not discuss that. This is one thing. Second thing is that there are so many, here you have 13 nodes, but you have to find out which node actually gives the best location for the placement of the shunt capacitors, right. But you have the load flow coding, say assuming that you have the load flow coding of a system, then you have to find out, there are several different ways are there to find out the best locations of the shunt capacitor or DGs also, right. But here I will tell you just I will explain that simple thing, that suppose to find out the base node of the which node actually is giving the best result. If it is a single capacitor placement, then it is not at all a problem, right. For example, suppose you consider node 2, right. What you will do, node 2, suppose I am just putting one graph. Suppose this is your this side is your say I am putting a connecting a capacitor say at node 2. So, this side is say QC2, right, and this side is the total power loss. This is the P loss of the network, right. So, what you can do is, suppose you are I am not putting it connecting it here, but suppose capacitor is connected at this node QC2. What you can do is then your load 2 PL, your PL2 plus it will become actually JQL2 minus JQC2, because I am connecting capacitor QC2. In the load flow data, right, you just increase the QC value in a step. Suppose QC2 in a step 10, 20 like this, you go on increasing, and this side use your QC2, go on increasing. Then what you will get? You will get a graph like this. It will be something like this, and this will be your minimum loss for capacitor, and this is the optimum value of the QC value, right. Similarly, remove this capacitor from node 2, remove this just one at a time, connect another capacitor at node 3, and again you if you plot the graph, then again somewhere it will start and again it may go further down, right. This way, although you need not plot the graph every time. So, what you have to do is that you have to see that when you write the code, actually you have to see this loss is decreasing, right. So, I mean this is the first point, this is the second, this is third. If you take the difference of the current minus the previous, then it will be negative. So, as long as the difference is negative, it is decreasing. As long as it is positive, just previous point you stop, right, and that is QC2 value, and this is the loss, right. Similarly, for each one at a time you have to take, and you have to find out of all this which one is giving you the minimum value of the loss, and corresponding capacitor value kilowatt. This is actually kilowatt, this is a kilowatt, and this is actually your kilowatt, right. You will find that which is the best value of the capacitor for single capacitor. If it is 2 or 3 capacitors, then of course you have to go for some optimization technique, that is the beyond the scope, right. So, and it does not necessarily mean that at the end node will be the base location, no, right. It will be some place where it will give you the your what you call that best minimum power loss, but at the same time one has to consider that your what you call that improvement of the voltage, right, that also it will be there. So, those things if you take 2 or 3 capacitors, fixed switch combination, those things are complicated, but this is what one can solve the capacitor optimization analytical technique. But the way I have told you that load flow 1, it is very easy one to write the code, right, but exam purpose you did not write code, but I am just telling those who are doing BTech project or this even master project also, many are doing like this load flow another thing. So, this will help you a lot, right. So, anyway, with this I do not know whether I have missed anything or not regarding this application of capacitors to the system, right, but with this we will go to the new topic, right. So, capacitor thing is over, good assignment problem will be given to you, right, and your job is to solve those things, have patience and you have to solve those things, right. With this that application of capacitors to distribution system, everything is covered now, right. So, after that we will go to the load frequency control chapter, and I hope this load frequency control just try to understand this, right. I will move very slowly for this one because it is a control system will come here, right, and you have all studied control system. And second thing is state space analysis, and you will find things are easy, but we will see that you are understanding each and everything. So, before moving to that, what I is supposed to tell you that generally in a power system, right, or we call here I have written electric energy system, same thing, right. Generally you will find that loads are changing continuously, right, increase decrease all the time, right. Some loads are switched on, some loads are switched off, it is continuously changing, right, throughout the day sometimes. But if you consider in a small your perturbation type of thing, small change in load, but that is all the time happening. Suppose sometimes we are switching on the you are switching off the your switch point at home or industry also, in off peak hours loads will be switched off, right. So, this at that time you will find that there is, if there is a very load flow studies, we have seen that in the power system analysis course, that decoupled load flow, right. In the decoupled load flow, that your if real power changes, right, if real power changes, then your voltage angle is changes, right, and it leaves the bus voltage magnitude I mean almost unaffected, and if voltage angle change means the frequency is changing, either the f or omega, the way you take. And if the similarly, if the reactive power changes, right, there is small change in reactive power, then voltage magnitude will be affected, but it leaves the your what you call voltage angle delta or the frequency. So, these two things are totally decoupled, right, for small changes. So, similarly, your same concept or same philosophy will be applied here, and later will come what is load frequency control, right. In general, actually, before moving anything, that sometimes we use the term automatic generation control, right. Actually, whatever I have understood, right, that automatic generation control actually is equal to load frequency control plus economic load dispatch together, right. So, if economic load dispatch is not there, then automatic generation control is equal to load frequency control. Why? Idea is something like this, that suppose you have a thermal unit, right, only I will considering about thermal units. So, every thermal units from our optimal operation of power system in the last your course, we have seen that every generator has a your cost characteristic, right. Suppose your load demand has suddenly increased to say from 1000 megawatt to 1100 megawatt. So, there is 100 megawatt increase of the load, and suppose in the power system you have 4 or 5 generating units, right, and each generating units, they have different cost characteristic. Then according to then you have to that 100 megawatt load you share among the 5 units in such a fashion such that your operating cost will be minimum, right. That means economic load dispatch is coming. So, that is why automatic generation control is equal to load frequency control plus your economic load dispatch. But economic load dispatch will not be there because already taught in this your previous course. And second thing is that economic load dispatch and automatic generation control, if both are combined together, then it may not be a classroom exercise, right. It will be a master thesis exercise or master course. So, only we will take the load frequency control. So, thank you very much.